We're going to continue talking about Chapter 14, in this section, concentration of solutions. And so we know that you can actually express how strong or dilute a solution is. Think about when we buy milk, 1%, 2% skim milk. We're going to go into some ways we talk about percentages and how much something of a compound is in a solution. So we know that 0.1 molar HCl solution, with a big M here, is going to be a dilute. Concentrated would be something that's about 12 molar. So this is coming straight out of the bottle. These are the 5 ways we're going to talk about concentrations in this chapter. This video is going to go in the top 4. We're going to save molality for later. Looking at these symbols and definitions, you can see they're very similar. We're now going to go through examples and checkpoints for each of the top 4: mass percent, mass volume, volume percent, and molarity. Be sure to pause during the checkpoints to make sure you understand these concepts. Let's first start out with mass percent. Calculate the mass percent of sodium chloride in a solution prepared by dissolving 50 grams of sodium chloride in 150 grams of water. So we know our knowns here are going to be our 50 grams, our 150 grams. In order for us to get the total mass of the solution, we're going to add those numbers together. Using our formula on the last page, mass percent equals mass solute over mass of solution. We put in our numbers and we can see that this would be a 25% mass by mass solution of sodium chloride. Try to do this checkpoint on your own. What is the mass of sodium bicarbonate needed to make 350 grams of a 12.3 aqueous solution? So here you can see we switch the variables, but we're going to still work on the same formula. So let's rearrange that. This should look very familiar. We went over this one in lab earlier in the semester. Here, so we have our 12.3% times 350, our mass of our solution, divided by 100, giving us 43.1 grams are necessary to make this solution. And you can actually go back and check 43.1 over 350, right? The next one's going to be mass volume percent. Saline is a 0.9 mass volume sodium chloride solution. What mass of sodium chloride is needed to make 50 milliliters of saline? So we have our knowns from the problem. We're going to use the equation, grams of solute over milliliter solution times 100. And remember, this multiplied by 100 factor is just to get our number in a percentage. So we're going to rearrange here, looking for our mass of our solute. Mass of solute, 50 times 0.9 over 100, giving us 0.45 grams of sodium chloride. Remember, the equation here on the right that I have up there in the formula section is just the same one on the left, rearranged to isolate the variable we're solving for. Here's a checkpoint. What volume of a 3% H2O2 hydrogen peroxide solution will contain 10 grams of hydrogen peroxide? Our knowns here are 10 grams and 3% mass by volume. We're again going to solve for our total volume of solution, rearrange our equation, put in our numbers, 10 grams over 3% times 100, giving us 330 milliliters of solution. And we actually should take out that decimal point. What volume of soda that is 6% by volume alcohol contains 200 milliliters of ethanol? Same thing with these, same setup. We're going to look at our volume of solute over volume of solution. Here we'll rearrange to solve for the bottom. Put in our numbers, 200 divided by 6 times 100, giving us 3,300 milliliters of soda. Volume percent checkpoint. A solution is prepared by mixing 200 milliliters of propanol with enough water to produce 400 mils of solution. What is the volume percent of propanol? It's only going to be 5% here. This one's very straightforward. Looking at 20 over 400 times 100, giving us 5%. The last one we're going to talk about in this video is molarity. And this is something a little new to us, but we know the solutions in lab that we've talked about have had a big capital M, and that is standing for molarity. Don't get confused between moles and molarity. Mole still needs to be written out MOL. Molarity is going to be capital M. And so if we wanted to make a 1 molar potassium chloride solution, we need to weigh out 1 mole using a balance, add them to a flask, and then fill it with enough water to reach 1,000 milliliters. So we would have 1 mole in 1 liter, 1.0 molar. So let's look at some examples. Calculate the molarity of a solution prepared by dissolving 9.35 grams of potassium chloride in enough water to prepare a 250 milliliter solution. So here our knowns are 9.35 grams and 250 milliliters. So here we're going to need to do two things with our numbers. Our first step is going to be converting our 9.35 grams to moles, and then converting 250 milliliters to liters. So we're first going to use our molar mass, 9.35 times 74.551 over underneath moles. So we have 1 mole over the molar mass. We now have 0.125 moles of potassium chloride. We divide that by our 0.25 liters. Remember, we have to have our number in liters on our denominator, so 250 becomes 0.25, and we've now made a 0.502 molar solution. How many grams of potassium hydroxide are required to prepare 600 milliliters of a 0.45 molar potassium hydroxide solution? We have 15.1 grams as the answer. Let's see how we got there. Here in this case, I gave you your molarity and your total volume, so you needed to work backwards to figure out how many moles are in there and then convert that to grams. So in this case, we're going to see our moles of solute equals 0.45 times 0.6, giving us 0.270 moles of potassium hydroxide. We're then going to multiply by its molar mass this time to give us our total amount of grams. And again, for all these questions, you can plug back your answers into formulas and double check to make sure everything works out. That's the end of concentrations.